The Higgs boson, also known as the God particle of the Standard Model of Particle Physics, is a crucial piece of the puzzle in understanding how the gravitational force works in the realm of physics. To truly grasp the significance of the Higgs boson, we must first understand gravity itself. Gravity is the mysterious force that attracts objects towards each other. It is what keeps us grounded on Earth and shapes the movements of planets and stars. For centuries, scientists have been questioning the origin of this force, and the discovery of the Higgs boson has brought us one step closer to unlocking its secrets. But how does this connect to gravity? The Higgs field has been hypothesized to have a connection with the gravitational force. Some theories posit that gravitational interactions between particles arise due to their interaction with the Higgs field. In this way, the presence of the Higgs boson may play a role in generating the gravitational force. Predicted to exist by British physicist Peter Higgs in 1964, and first discovered in 2012 by the Large Hadron Collider, LHC, in Switzerland, this remarkable particle is associated with the Higgs field, which permeates all of space. Imagine this field as an invisible ocean, through which particles swim. As massless particles move through the Higgs field, they encounter the Higgs boson, gaining mass as they interact with it. This interaction, known as the Yukawa interaction, is what gives particles their mass and inertia and allows gravity to exist. Now, on to the next key player, the Yukawa interaction. Proposed by Japanese physicist Hideki Yukawa in 1935, this interaction explains the attractive force between fundamental particles that have no mass along with the strong nuclear force that holds the particles of an atom together. In modern physics, there are four fundamental forces: gravitational, electromagnetic, strong nuclear, and weak nuclear. The Yukawa interaction specifically relates to the strong nuclear force and how it interacts with elementary particles called mesons, a type of boson force carrier particle. Massless particles that acquire mass, such as quarks and leptons, fundamental particles of matter known as fermions, do so through the Yukawa interaction and the Higgs field with the exchange of a meson particle. Similarly, the exchange of meson particles plays a role in holding together the atom. Massless particles like photons do not interact with the Higgs field and therefore always travel at the speed of light. The strong nuclear force is responsible for holding protons and neutrons together in an atomic nucleus. It is a very powerful force, but it only acts over extremely short distances. The Yukawa interaction explains this behavior by stating that the force between two mesons decreases exponentially as the distance between them increases. This means that the force becomes weaker the farther apart the mesons are. So, how does this relate to the gravitational force? Well, the gravitational force is also said to have a similar behavior, but on a much larger scale. Like the Yukawa interaction, the gravitational force between two objects, such as planets or stars, decreases with distance. However, unlike the strong nuclear force, the gravitational force decreases according to the inverse square law, not exponentially. But how do the Higgs boson and Yukawa interaction combine to form gravity? Well, when particles gain mass through their interaction with the Higgs boson, they become subjects to the force of gravity. The mass of an object determines how strong its gravitational pull is, so the more mass a particle has acquired from the Higgs field, the greater its gravitational influence. In this way, the Higgs boson enables particles to possess mass and inertia, and the Yukawa interaction generates the attractive force between them, ultimately shaping the force we know as gravity. It is important to note that the exact relationship between the Higgs boson and gravity is still an active area of research. While the Higgs field and boson are significant in explaining mass, further exploration is required to fully understand their influence on gravity. Nonetheless, the discovery of the Higgs boson has offered important insights into the fundamental workings of our universe. Understanding the connection between the Higgs boson, the Yukawa interaction, and gravity is a crucial step in unraveling the mysteries of the universe. It sheds light on how particles gain mass and why objects are drawn together. This knowledge not only deepens our understanding of the fundamental forces of nature but also paves the way for further advancements in physics and cosmology.